Hello, let's start off with some review board questions. So try them out before I do them. If the speed of sound is at and the tuning fork is 900 hertz and held over a closed tube, cool, very important information. So it's a closed tube, 900 hertz speed of sound, and the length of the tube is varied, what would be the length of the first three resonance nodes that would be heard? So if it's a closed tube, we're going to hear it at a quarter of a wavelength, we're going to hear it at 3/4 of a wavelength, and we're going to hear it at 5/4 of a wavelength. Those are the length of the tubes. So first thing we need to do is find our wavelength. So we're going to do V divided by F. So if we do that, we get 343 divided by 900, and that's going to be our wavelength. So I just have to take that value and times it by a quarter. So that's my first wavelength, and then take it and then multiply it by 3/4. That's my second one, and then my third one is going to be 1.25, and those will be my three links. So I just match them up. 286, 473. So A is the correct answer, right? So all we're doing is this is a quarter, this is 3/4, this is 5/4. Those are the first three resonance zones or resonance points. Okay, and then a 266 hertz tuning fork is used in experiment in a closed pipe. So we have frequency, closed pipe. The first resonance is located when the pipe is that long. As the pipe is shortened, the next resonance point is that long. When the pipe is that long, the data indicates that the speed of sound is. Okay, so let's draw this out. So it's a closed pipe again. So it's saying that this length here is 0.687, and then this length here is 0.412, like that. So we know that in between the resonating points is half a wavelength. So what we can do is we can take that 0.687, we can subtract 0.412, and find this length in between here, which is 0.275. Right? And we know that that's half a wavelength in between those resonating points. So if we want to find a full wavelength, we just have to take that value and we multiply it by 2. So that's how long our wavelength is. And then we just have to use V equals lambda F to find our speed of sound. And if we multiply it by 622, we end up getting 342.1. So our 3-digit answer would be 342 as our answer. Okay, so today we're going to talk about Doppler effect. It's a nice short lesson, not as long as the last one there. So the Doppler effect refers to the apparent change in frequency of a wave from its original frequency when the wave source or the wave observer are moving relative to each other. So what this is the sound of a fire truck as it's moving. The frequency changes, right? When if a fire truck is coming towards you, it's like like that. So the siren sounds higher in pitch when the truck is coming towards you and lower in pitch when the fire engine is going away from you. So here's a video that shows that. So let's watch this video. Okay, it sounded like the pitch, the frequency of the note changed, but if you've ever honked a horn inside of a car, well, it doesn't change, right? A horn just makes one noise. So what that means is that the person inside of the car and the person outside of the car don't agree on the fact of what the note is. They don't agree on the same frequency, because if you're in the car, you're stationary relative to the horn, and if you're outside of the car, you're moving relative to the horn. So you have different perspectives. So I can explain the Doppler effect really easy just with this picture. So the thing about sound waves is sound waves move about 340 meters per second. Depending on temperature and humidity, though it'll change a little bit, but roughly 340 meters per second is the speed of sound. So that's if the air doesn't change, if the temperature, the humidity doesn't change, that's what the speed of sound is. So well, let's talk about a bus. So if I'm on a bus, this is my bus, and this is me, and the bus is moving at 10 meters per second, and then I'm moving to the front of the bus at 1 meter per second. If someone was watching me out here and they said, well, how fast am I moving? Well, I'm moving at 11 meters per second, right? Because I'm moving with the bus. So that's how particles, that's how objects work. But waves don't work that way. This is the speed of sound, regardless of if you're moving or not. So let's say that this cop car is moving at 10 meters per second, and these waves want to travel out at 340 meters per second. Well, these waves can't move 350 meters per second. That's not how it works. They have a certain speed limit. That's how waves work. So what happens is, because these waves are flying out of here with that extra speed, they end up bunching together. The analogy that I use is, picture you're moving through the school hallways, okay? And the hallways are filled with lots of people, and all those people are moving really slow. And then you are late for something, so you come behind them, but they're blocking you in every way. So what happens is you end up slowing down and going the same speed as them. If people are coming behind you that are trying to go faster, what's going to happen is you're all going to start bunching up, and that's what happens. So those waves, if this was our original wave, they start getting closer together. And the opposite happens on this side. As those waves are coming off, they get stretched out because the police car is moving away, but they're still trying to go 340 meters per second. So these waves get longer, and these waves get shorter. So the shorter wavelengths make a higher frequency, right? When we decrease the wavelength, we increase the frequency, and then these bigger wavelengths, right, it's going to decrease the frequency, so this is a lower note. So that's why when the car is coming towards you, it gets higher, then it gets lower as it passes. So this person hears a higher note, this person hears a lower note, and they don't agree on what the note is. And the person inside of the car hears the actual note, so none of these three people agree on the note that's playing. So this is our formula for doing the Doppler effect, and this is probably the most confusing formula that we do all year. So F is the frequency detected by our observer. So this is what we call a lot, our apparent frequency. This is the frequency that these people hear. Okay, so our apparent frequency is F. Fs is the frequency of the source, and that's the frequency that the driver hears. So yeah, they're both F, and it's kind of confusing. And then we have two V's in here. V is the speed of the sound wave, and then Vs is the speed of the source. So this would be the speed of the car, and then this would be the speed of the wave. Okay, very confusing. And you'll also notice this very lovely plus minus. This is harder to do. I have a way of remembering when to use plus and when to use minus. It's easier to do in class, but what I usually do in class is I pick a student and I tell them, I want you to tell me the emotions that you feel as I do this next thing. How do you feel? Do you feel good, or do you feel positive, or do you feel negative? Which sounds kind of weird, but it's not weird, I promise. So then they're like, okay. And then they are sitting in their desk, and what I do is I run towards them and I go, as I'm running towards them. And obviously the feeling that they get is negative, because that's a horrible noise. And I'm like, okay, now compared to the first one, tell me what you're feeling. And then I go, ah, and I run away from them, and they feel more positive. So I use that to remember, but it's harder to do virtually. So you use positive if the source is moving away from the observer, and you use negative if they're moving towards. So picture me screaming, running at you, and the negative feelings you get if they're moving towards each other. So let's do an example with this formula. So an opera singer is singing and holding an F note at a frequency of 431 hertz. The speed of the sound wave is 340 meters per second. Determine what speed and direction the parade float is moving relative to you for you to hear a G note. So it says that the opera singer is holding an F note, but we hear a G note. And then here's a little source to help us here. So this is the note that they're playing, and this is the note that we hear. So what we hear is we hear a higher note. And if we hear a higher note, that means that they are coming towards us. If we heard a lower note, that means they're moving away from us. Okay, so that's what we have. So now we can use that formula and we can rearrange it. So I'm going to switch to this screen here. So our formula is F equals Fs V over V plus minus Vs. This is how I usually write it, which is a little bit different than it's written, but I find that's a nicer way of writing it. So we found that they're coming towards us, which gives us negative feelings, so we know that's going to be minus. And what we're looking for in the question is we are trying to find, determine what speed and direction the parade float is moving. So we want to find the speed of the source. Okay. So we can move these guys as long as we move them together. We can move V minus Vs up top, and we can move F down below. And then we can subtract a V from both sides. And we still have this negative here, so I'm going to make this positive, I'm going to make this negative, and I'm going to make this positive. So now I have the speed of my source is equal to the frequency of my source divided by my apparent frequency plus the speed of sound. So that's my equation. So they tell us that the frequency of the source is, that's the actual frequency is an F note. And in that chart, it tells us an F note is 341.3 hertz. And this V is the speed of sound, which they tell us to be 340 meters per second. And this F down below is our apparent frequency. So we hear that as a G note, and a G note on our chart is 384 hertz. And we have to add on the speed of sound to our answer. So when I plug that all in, 341.3 times 340 divided by 384, and then I add on 340 meters per second. Oops, I forgot one thing, right? When I made this positive, I forgot to make this negative. Sorry about that. So let me try that again. So 341.3 times 340 divided by 384, and I need to make that a negative number. So I end up getting negative 302, and then I add 340 onto that, and it tells me that my answer is 37.8 meters per second. So that's how fast the parade float is moving. Okay. So another question that we have. An opera singer is still holding an F note. If the parade float motor went out of control and it accelerated it to a speed of 68 meters per second, what note would the parade attendees hear as the opera singer drove away? Okay, so let's write out that formula again. So that formula is F equals FSV, V plus minus Vs. That's our formula. So now it's moving away, which gives us positive feeling. So that one's a positive. And it's asking for what note would the parade attendees hear. So we want to hear what is that apparent frequency. So we don't have to rearrange this at all. So she's still holding that F note, which is 341.3 hertz. Oops, did I forget the 0.3 last time? No, I didn't. Good. 341.3 hertz. This V is the speed of sound, which is still the same as the last question, which is 340 meters per second. And then we do the speed of sound again, 340 meters per second. And we want to add on the speed of the source, which is 68 meters per second. So if we plug all of that in, remember that we add these on the bottom here, we don't multiply them. So we get 284.41, 6 repeated hertz, and it asks us what note that is. So if we go back and we look at our chart, so it looks to be closest to a D note. So we would hear a D note. Okay. So I have a board question for you, so give this a go. And yeah, pause the video, and then I will go through it. So a fire truck approaches you at 20 meters per second, and you hear its siren to be 366. So this is our apparent frequency, so this is F. We want to hear the actual frequency, what the real frequency is, so that would be Fs, that's the frequency of the source. So we're trying to find frequency of the source. So this one we will have to rearrange. So this is our formula again, it's plus minus, and it says in the question that the fire truck approaches you. So that's going to be negative. And we are trying to find this. So we can move V minus Vs up top. And then we can move V down below. And that's what we would want. So V is the speed of sound, which is 343 meters per second in this question. The speed of the source is 20 meters per second. The frequency that we hear is 366 hertz. And then the speed of sound again is 343 meters per second. So just think about this for a sec. So the truck is approaching you and this is what you hear. So if it's approaching us, we should hear a higher note than it actually is. So we're expecting something less than 366. Try to use your common sense with these questions, and it can help to know if you did something wrong or you put a negative where it shouldn't be. So we get an answer of 345 hertz, and that makes sense. So this is what it actually is. We hear this, which is a higher note, so that makes sense that that's what we would get. So when looking at stars from Earth, you would expect some stars to be moving towards us and some to be moving away, right? It's kind of like if you stood in the middle of a road and you were looking at cars pass by. Some cars would be moving towards you, some cars would be moving away from you. That's what you would expect. But with stars, you don't actually get that. When scientists look at stars, they see that almost all stars are moving away from us, which is weird. Well, how do they figure that out? Well, they look at it through a spectroscope. So if this is a regular light wave. So this is a wave of light. If the star is moving away from us, it's kind of like the Doppler effect, where what it does is it stretches out that wave. It stretches it out and makes it longer. If the star is moving towards us, it makes it more compact and scrunches it together. So red light has a certain wavelength of 700 nanometers. Blue light is 400 nanometers. So what that means is a red light is longer. So when that light wave gets stretched out, we call it a redshift. And when the light gets smaller, gets squished together, it's a blueshift. So when the star is moving away from us, we call it a redshift. When the star is moving towards us, it's a blueshift. And it's not the actual color that we see. What we can do is we can look at a star, and we look at it through something called a spectroscope. And the spectroscope gives us these lines, and these lines represent different elements that it's made up of. So a stationary observer would see these lines for the different elements right here. If the star is redshifted, all these lines are shifted towards the red end of the spectrum. And if it's blue shifted, all the lines are shifted to the blue end of the spectrum. So if they look at a star, and this is what it should be if it was stationary, but all these lines are shifted to this side, it means it's moving away. And if they look at it and it's like that, it's moving towards. So scientists saw that, oh, all stars are moving away from us. That's weird. How do we explain that observation? So the way that they explained it is that, well, most stars are moving away from us because the universe is expanding. I had a little demo to show this. Yes. Here's my demo. So I'll switch cameras. So here's a balloon. And you can see I've drawn little dots in the balloon. So they're pretty close together. So the only way that I can get these dots to all move away from each other is if I blow them up. So now all the dots are a little bit further away. Now all the dots are even further away. Now all the dots are even further away. So as this balloon expands, every single dot gets further away. And that was a great explanation for what's happening. So the universe must be expanding. So by calculating the speed of expansion, well, if it's expanding, it must have come from a single point. And that's where the idea of the Big Bang theory, not the show, but the actual theory, was that everything was at one point in the beginning of the universe, and then the Big Bang happened and sort of exploded everything, and we're just expanding from that Big Bang theory, from that Big Bang. Okay, so this is our homework. Not very much homework, Doppler effect stuff here, and here's some unit review for you to work on, because this is our last lesson in the unit, and we have our unit exam after this. So yeah, shoot me an email if you have any questions, and that is it.